Good afternoon, everyone. My name is Kevin Menard. I'm a principal member of technical staff at Oracle Labs, which is a research group within Oracle. And I'm here today to talk to you about fast metaprogramming with Truffle. Before we get started, I need to inform you that what I'm presenting today is research work out of a research group. It should not be construed as a product announcement, and you really shouldn't buy or sell stock in Oracle based on anything you hear today. All right, with that out of the way, let's get back to fast metaprogramming with Truffle. We'll start by focusing on what Truffle is, since I'm guessing a lot of you are not familiar with it. So Truffle is a framework in DSL for writing self-optimizing AST interpreters. It provides a lot of the common tooling needed to build out a language VM, such as debugging and instrumentation. And it provides some facilities for writing and optimizing AST interpreter, such as cache control and node splitting, type specialization. And Truffle can interface with Graal, which is an optimizing JIT compiler. And the combination of the two will perform partial evaluation across the AST interpreter to generate highly efficient machine code for your program. For those of you that aren't familiar with half of what I just said, the basic idea is when you're building a way to execute a dynamic language, you often start with an AST interpreter. They're very easy to build and very easy to reason about, but they often suffer from performance issues. And a lot of languages go through this evolution where they start with an AST interpreter, they hit a performance wall, and then they try to build out a bytecode interpreter or their own compilation phases for their language, or they'll integrate with something like LLVM and try to make use of its JIT facilities. But then they still have all the other stuff necessary to build out a language VM, like a debugger and whatnot. So the Truffle philosophy is you just build an AST interpreter, and you keep that very simple implementation, and we handle the optimization part for you. And you're able to basically maintain the simplicity of the AST interpreter by annotating a little bit, but you gain everything you would typically gain by building out a full language VM. So Truffle gives us a way to build out support for dynamic languages, but Ruby is a very large language. It has a very rich core API. So what we've done is we've pulled in code from both the JRuby and Rubyists projects, and we're actually part of the JRuby project. Everything we do is open source. We're an alternative backend, and we've been shipping with JRuby since JRuby 9000. If you use this -x+t switch, you can activate our backend. Now, while we're not quite ready for production usage, we're hardly a toy implementation either. We currently pass 90% of the core library specs for Ruby spec, 92% of the language specs, and because Ruby spec has a lot of holes in its coverage, we've been putting an emphasis on trying to run actual libraries, and we're now able to pass 99% of the tests for the stable version of active support. All right, so with Truffle out of the way, let's turn our attention to metaprogramming. Metaprogramming has existed for a long time in a variety of languages, and it's a core component of Ruby. Unfortunately, it seems to almost defy definition. If I asked each of you to define metaprogramming, I'm quite certain I would get back different definitions from all of you, some of them potentially conflicting. Seems to be one of these things that you know it when you see it. So for the purposes of this talk, I'll restrict the definition of metaprogramming to be the dynamic modification of objects, including classes, and the generation of code at runtime to execute dynamically. And moreover, this usage will be limited to Ruby's reflection and evaluation APIs. Again, that was quite a mouthful, but basically, if you've used add or accessor to generate helpers to load and store instance variables in an object, we won't consider that metaprogramming. The act of generating the accessors would have been, but using the generated accessors to get or modify that state isn't metaprogramming. If, on the other hand, you had used instance variable get or set, which are reflection API methods, then that would be metaprogramming. And Ruby has a very rich metaprogramming API. It's not explicitly called out as such, and it's not cohesive. These methods appear in several classes and modules, but they provide the functionality for what we consider to be metaprogramming. All right, fast. Fast in Ruby is a very contentious term. I've been doing Ruby since about 2008. I'm sure many of you have been doing it longer. But the number of times I've seen this battle waged between developer productivity and execution efficiency is mind-boggling. And I don't know if this is a case of a vocal minority that wants to somehow pit these as two opposites of each other, but they needn't be. So there seems to be this belief that if you want to write concise, elegant Ruby, you have to sacrifice performance. And on the converse, if you want something that runs fast in Ruby, it needs to be ugly. So for fast, we want to satisfy both conditions. It should be elegant and it should perform well. All right, so now fast and metaprogramming. These are two words that aren't often seen together. And that's because if you've ever done metaprogramming in MRI, you've probably noticed performance something like this. So what I've done here is implemented 4 micro benchmarks, and they are micro benchmarks, so please take the usual set of warnings that come along with that. But what I've done is measured method dispatch time using static dispatch, and just calling the method directly, and metaprogramming, calling it through send. The time required, or the time spent loading and storing instance variables using the generated helpers from attr accessor, and doing the same thing with instance variable get and set. And then I implemented a simple object proxy using method missing. So in this case, I had a wrapper that just wrapped around string and ultimately delegated to string.length. So in the static dispatch case, there's a method defined that does the delegation. And in the metaprogramming case, that same delegation is performed using method missing. And what we can see is for method dispatch, it's about 2/3 as slow, or 2/3 the speed to call with send. Instance variable getting and setting are roughly the same. I mean, there's a hit there, but these are also optimized calls in the YARV bytecode instructions. But for method missing, there's a pretty substantial hit here. Now, running these same benchmarks with JRuby+Truffle, we've virtually eliminated all the overhead associated with metaprogramming. The numbers here do skew a bit more than on MRI because we have a jitting compiler, and some of that runs non-deterministically. I took the average of 3 runs here, but there's a skew of maybe 5% on the score. Just to demonstrate that I didn't do some kind of trickery here, because I could make them match quite well if I didn't really optimize anything. I've compared the cost or the performance of MRI's static dispatch and metaprogramming against running the same code with JRuby+Truffle's metaprogramming. And what you can see is for method dispatch, we're about 4 times as faster. For the instance variable operations, we're about 5 times as faster. And for the method missing case, about 10 times as fast. Okay, so does it matter? Ruby's been around for 20 years. No one has really seemed to be bothered by this performance gap. We're a research group. We just kind of invent a problem to fix. So I wanted to take a survey of how frequently metaprogramming calls are made. And for this, I looked at MRI's standard lib directory. I looked at the most recent stable version of Rails, and then I ran a GitHub code search. I can't show all the values for all the metaprogramming methods, so I took a sample here. And what we can see is MRI is fairly conservative in its usage of metaprogramming within standard lib. It does make rather heavy use of respond to, but for the most part, it doesn't make that many metaprogramming calls. Rails amps it up a little bit, and then the GitHub code search shows that Rubyists across a wide variety of projects like using metaprogramming calls. The GitHub code search results are a little noisy. I'm subject to whatever GitHub code actually indexes and how they facet their data. For instance, in the respond to case, I couldn't even include results because GitHub code search doesn't index question marks, and Rails happens to have its own respond to helper that does something completely different and was filling up the results here. Of course, having methods being called doesn't give you the whole picture. It helps paint it a little bit, but we could have a small number of metaprogramming calls made on very hot execution paths, and we can have a large number of calls made in execution paths that simply never execute. So I wanted to see, where these metaprogramming calls are actually being made. And just a little sample here, in NetHTTP, if you post a file, you could be calling respond to up to 4 times, each of these doing the method lookup. If you use the delegate library, that just uses metaprogramming everywhere. Matrix uses send inside of a loop. And in Rails, there's 2 really hot cases. Rails has this class called time with zone that's used virtually everywhere. And Active Record has these find by column helpers. And those themselves have a very interesting history with performance. They're implemented using method missing. And for instance, in JRuby, method missing won't JIT. So I've seen several projects move from using these find by column name helpers to using Arrow's where clause, which will JIT, but then the find by column helpers got a nice little cache added for them that may have overtaken the performance advantage of being able to JIT. They're still being done by method missing, but at some point someone else added this feature in the method missing handler that dynamically defines the helper method on the model class, so you don't have to go through method missing the next time. But adding a method to a class can invalidate inline caches, and eventually things stabilize. But the point is there's been a lot of work around trying to deal with the fact that metaprogramming just doesn't perform as well as static dispatch. And I think this is an unfortunate consequence of not having really looked at the problem. And to just kind of illustrate this a bit more, in the Bench 9000 suite, which is a benchmark tool, part of the JRuby project, we have a benchmark using psd.rb, which is a Photoshop file processing library. And it happens to make heavy use of metaprogramming on its hot execution paths. And what we can see here is JRuby+Truffle is about 33 times faster than MRI, and a good deal faster than most of the other Ruby implementations. That's not completely, entirely related to metaprogramming, but a large portion of it can be attributed to that. All right, so what makes JRuby+Truffle different? Why are we able to eliminate metaprogramming overhead while other implementations seem not to have been? If we take a look at this metaprogramming API, at least a subset of it, you'll see that there's a very common structure here. And that's that they often take some form of name as the first argument. That could be a method name, a variable name, a constant name. But there's some way to discriminate what they're ultimately going to be doing. And this has a very strong parallel to Ruby method lookup. So method lookup in dynamic languages is kind of a slow operation. In Ruby, it's a really slow operation because Ruby has a very rich class hierarchy. So when you call a method, it could be coming from the class. That class is singleton class, a superclass is singleton class, mixed in modules, and so on. So when you call a method, if it's at the root of your ancestor tree, you're traversing quite a few lookups to get it. And in isolation, this doesn't seem that slow, but the compounding factor here is everything in Ruby is a method call. If you add two numbers, that's a method call. So you have an insane number of method calls being made, and each of these would have to do this costly lookup. So what we do is we cache that. The basic anatomy of a call site, which is where you'll be making a call from, is you have a receiver, you have the method name, and then you have arguments for that method. And you can also have blocks, but I've kept that out of here for now. It doesn't really add anything. So first level of caching is typically a global method cache. And what you have is a lookup table that's keyed by the receiver class and the method name. And the value ends up being a function pointer that ultimately represents the method you're going to execute. So what I've shown here is a very simple example in Ruby where we subclass string. And on a string instance, we call .length. On that subclass, we also call .length. And then we try to get the string length by going through send. And in the lookup table here, what you can see is for string length and my string length, they have the same exact function pointer value. And that's because we didn't override length in my string. So it's going to use string's definition. So the next time we encounter a my string object that calls length, we'll be able to find it in this lookup table and avoid searching through its ancestor tree. But in the send case, we have a different value in the lookup table. And that's because what we're caching is the send method, not the thing send is ultimately going to end up calling. The global method cache suffers from several issues. So we want it to be fast. If it's not fast, we may as well have just done a full method lookup. So one of the key things we need to do is constrain its size. In MRI, the global method cache has a default size of 2048 entries. Should you get to that 2049th method, which you almost certainly will running something like Rails, you're going to have to evict something from the cache. And you also have to do a full method lookup so you can get the value that you're going to insert in the cache. But the cache eviction itself also has to be fast. So in MRI, for instance, there's this deterministic algorithm for it, but there's no way for you to exploit it. It's not an LRU cache or anything meaningful. So you can have two methods back to back in a loop that end up basically overwriting each other, even though you have 2,047 other potential slots to write into. Additionally, Ruby's highly dynamic. So you can add or remove methods, redefine them. You can dynamically mess with an object or a class's hierarchy. And when this happens, it can invalidate your cache results because the method that you have cached might not be the one you need to call the next time. And we don't want to trace the ancestor hierarchy for each of these cache entries, so we just flush it, the entire thing. And this can lead to some really pathological performance issues. The solution for this is to localize your caches. So we have this thing called an inline cache. And I have basically a kind of weird pseudocode Ruby thing here to help illustrate the point. But at a call site, when we call a method, what we want to do is store that cached method pointer right with the call site. And because Ruby is a dynamic language, the receiver type can change. So we need to guard this cached lookup with a check that the receiver class hasn't changed. We have to guard that the type of the receiver hasn't changed, and then that the receiver's class and its ancestors also haven't changed. So you have these two guards in place. There's been a lot of work looking into this in Ruby and other languages, and the overwhelming majority of call sites are monomorphic. So this lookup will almost always pass after it's been cached once. And what we can do is, now that we have the cache method pointer, we're able to just call that and avoid looking at the global cache at all, or doing that full method lookup. If either of the two guards fail, then we do need to go do the method lookup. This will likely hit the global method cache if the implementation has one. Then we update the inline caches and we call the method. So that's a brief overview of Ruby method lookup. So if you recall the slide with the metaprogramming methods, they had this name attribute and it's an argument, and we want to exploit that fact. So what we want to do is basically add a new dimension to our caching. And JRuby+Truffle does this using something called dispatch chains, which are basically just a generalized form of inline caching. And to make this a bit more concrete, what we have in this example is basically the outer if statement is the inline cache as we know it, but we've added an inner level of checking on the arguments themselves. So the example was calling object.send with length as the argument. So we're going to check that object is still a type myString, and that myString or any of its ancestors haven't changed. And then we're going to check that the cached argument is still length. And if we can do that, we can skip calling into send completely and call directly to the length method. So for the cost of an extra guard check or two, we're able to basically dispatch this exactly the same way we would have done if we called length directly. And then if the argument doesn't match, we can do the lookup again and basically update that argument cache internally. And what I'm showing here is, again, something that's monomorphic. It's a single cache entry, but you could extend this quite easily to handle multiple values, and you would just have a chain of if statements in that case. So JRuby+Truffle makes it really easy to implement these dispatch chains. What we do is, because we have an AST interpreter, we have specialized nodes for these operations. So that does mean for each of the metaprogramming API methods, we may have a specialized node for it, but the number of these methods is finite, and there's no way for Rubyists to introduce additional ones. So when we call the send method, we have a specialized send node that we use. For instance, variable get, we have a specialized instance variable get node. And they know what type of value they want to cache. So in the send case, we'll cache the method lookup. In the instance variable get case, we'll cache the location of the field we want to retrieve in the object model. And because Truffle has this very handy feature for implementing these dispatch chains, we're able to do this very cheaply. In addition, I had shown that when the cache needs to be invalidated, we have this else clause that does the lookup and then updates the cache. In JRuby+Truffle, when combined with Graal, we're able to eliminate that else statement completely, and we just de-optimize. So all of this compiles down, and we get these checks essentially for free through our assumptions. If the check is invalidated, de-optimization is a very heavy process, but we just can jump back into the interpreter and rerun everything. And then the final aspect here that Truffle really helps us with is method sharing. So if you envision that argument cache like an inline cache, the problem is it would be associated with the metaprogramming method. So if you were calling send, for instance, from 100 different places with 100 different arguments, you'd blow out your cache very quickly. What you really want is that cache value to be associated with the caller of send's call site. In MRI, this could be done with optimized YARV instructions, passing in additional state. But with JRuby JRuby+Truffle, what we do is because we have an AST interpreter, we just copy a fragment of the AST tree and then insert it someplace else for each of the different call sites and reset the cache along the way. And Truffle and Graal are able to manage this for us, so we don't have to do anything fancy. They determine when a cache is about to go polymorphic or megamorphic and can handle the splitting and rewriting for us. So that's about it. Rubyists like to use metaprogramming. We have 20 years of Ruby code to look at to demonstrate that, to prove that. And what I was trying to posit here is that metaprogramming should be fast. Our job as language implementers is to not penalize users for using features the language provides. We shouldn't come up with these weird rules around when you can and cannot use metaprogramming. We should just make metaprogramming fast. And I think we've demonstrated that metaprogramming can be fast. And we did this without modifying the language at all. So it's fast in the way that Rubyists have come to understand it in terms of developer productivity, but it's also fast now with execution efficiency. And that's about it. The solution here seems really simple, and it is really simple. But getting there took a lot of work, and the research done for it was presented at PLDI last year. The group that did it, they looked at performance in both Ruby and Smalltalk implementations, and they compared the results on meta-tracing JITs and partial evaluators and found that this general technique of dispatch chains works well across everything. JRuby+Truffle is the first and I think only implementation now out in the wild using these dispatch chains to minimize the overhead of metaprogramming. And again, getting there required collective efforts of a bunch of researchers and the JRuby and Rubinius communities and so on. So that's about it. That's my contact information. If you have any questions about this, please feel free to email me or tweet at me. We have a pretty thorough wiki page in the JRuby project, and you can always just do an internet search for JRuby+Truffle and find a variety of blog posts and whatnot out there. That's it. Thank you very much.
I actually have several minutes for the QA. Anyone have any question? Evan, yes.
Hi.
Hi.
What happens if, so you showed the sort of an example of what the two-level caching looks like, where you're also caching to say, oh, it was the argument length, right? Could you explain more about what happens when that starts to fail a lot? So, you know, the whole point of that send is that the argument could be different every time, and it very well might be. A good example might be the active record find by column. They may cycle through every single call to maybe a different actual method being called. So can you explain a little bit what happens in that case? Does it just give up after a while, or?
Yeah, so we treat it essentially the same way an inline cache works. So there hasn't been as much research in this area to prove whether or not the arguments themselves tend to be monomorphic, but we can support polymorphic calls. So we just have a cascading set of if statements. For the examples we've run thus far, they do tend to be a low number, less than 3. But in the case where you would have a large number, just like with an inline cache, you'd eventually mark it megamorphic and give up, essentially. So we give up after 8, basically right now, but it's tunable.
Any more questions? All right. Thank you, Kevin. Thank you.